What if everything we see, touch, and experience is just the surface of something far deeper, something invisible, yet woven into the very fabric of reality itself? The universe has always been a master of secrets, hiding its truest nature behind layers of mystery. But what if some of those secrets aren't just hidden in distant galaxies or buried in the heart of black holes? What if they're right here, all around us, unseen but undeniable, shaping everything from the atoms in your hand to the vast emptiness between stars? This is the world of hidden fields, forces, and phenomena so subtle, so pervasive, that they might just hold the keys to understanding existence itself. Think of space as an ocean. We're like creatures floating on the surface, aware of the waves and the wind, but oblivious to the immense currents moving silently beneath us. Hidden fields could be those currents, unseen forces guiding the behavior of particles, the expansion of the universe, even the passage of time. Some theories suggest these fields might explain dark energy, that mysterious force pushing the cosmos apart. Others propose they could be the missing link between gravity and quantum mechanics, two realms of physics that refuse to play nice. And then there are the wilder ideas fields that might allow for alternate dimensions, or even consciousness itself to be woven into the universe's architecture. This isn't just science fiction. These are real cutting-edge theories being explored by physicists right now, and that's what makes this journey so thrilling. Because if hidden fields are real, they could rewrite our understanding of reality. Imagine discovering that the universe isn't just made of matter and energy, but of invisible frameworks holding it all together, like the scaffolding behind a painting. Today, we're diving into 30 mind-bending theories about these hidden fields, from the well-supported to the brilliantly speculative. Some will challenge everything you thought you knew. Others might leave you with more questions than answers, but one thing's for sure, by the end you'll never look at the cosmos or the space around you the same way again. Even the emptiest corners of the universe are alive with activity. What we call empty space is anything but it's a seething, bubbling sea of energy where particles blink in and out of existence so fast they defy detection. These are quantum vacuum fluctuations, and they might be the first clue to understanding the universe's hidden scaffolding. Picture a calm pond at night. On the surface, everything seems still, but beneath, tiny fish dart, currents swirl, and unseen life thrives. The quantum vacuum works the same way. Particles and their opposites, antiparticles, constantly form and annihilate in bursts of energy so brief they're almost ghosts. Yet their fleeting existence could have enormous consequences. These quantum fluctuations aren't just background noise. Some physicists believe they give rise to hidden fields that shape reality at its most fundamental level. Think of it like static on an old television. What seems like random interference might actually carry a signal, a pattern we haven't decoded yet. In the quantum world, these fluctuations could influence everything from how particles behave to why galaxies hold their shape. One theory even suggests they're the source of dark energy, that mysterious force accelerating the expansion of the universe. If true, it would mean the very fabric of space itself is generating the push that's tearing the cosmos apart. But the wildest part, these hidden fields might not just be passive observers. They could actively interact with matter in ways we're only beginning to grasp. Imagine a dancer moving through water. Every step, every turn is shaped by the resistance around them. In the same way, particles moving through these quantum fields might experience tiny nudges, subtle shifts that change their behavior. Some researchers speculate these fields could explain why quantum mechanics and gravity refuse to fit neatly together in our current models. Maybe the missing link isn't a particle or a force, but an invisible framework humming beneath it all. The implications are staggering. If hidden fields born from quantum fluctuations really do underpin reality, it would mean the universe is far stranger and far more interconnected than we ever imagined. Every empty space, every moment of stillness could be teeming with unseen activity, shaping the cosmos in ways we're only starting to uncover. And that's just the first piece of the puzzle. The Higgs field isn't just some abstract scientific concept, it's the reason you have weight when you step on a scale. Picture an invisible cosmic molasses filling every inch of space, slowing down particles as they move through it. The more a particle interacts with this field, the more mass it gains. Electrons barely feel its tug, which is why they're so lightweight. Top quarks, on the other hand, slog through like they're wading through syrup, emerging as some of the heaviest particles we know. This elegant mechanism explains why the fundamental building blocks of reality have mass at all. Without the Higgs field, atoms wouldn't form, stars wouldn't ignite, and you literally wouldn't exist. But what if the Higgs is just the beginning? Some theories suggest our universe could be humming with other, even more mysterious scalar fields, cousins to the Higgs that haven't been discovered yet. These wouldn't give particles mass, but they might do something far more dramatic, shape the evolution of the cosmos itself. Imagine invisible rivers flowing through space-time, their currents subtly warping the expansion rate of the universe or the formation of galaxies. One particularly compelling idea is the inflaton field, thought to have powered the universe's explosive growth during the Big Bang. While the Higgs field deals with mass, these hypothetical fields could govern everything from dark energy to the very dimensionality of space. The mathematics behind these theories reveals something extraordinary. Such fields wouldn't just sit quietly in the background. They could oscillate, creating waves in the fabric of reality that might leave detectable imprints. Some cosmologists search for these fingerprints in the cosmic microwave background, the afterglow of the Big Bang. Others hunt for subtle variations in the strength of fundamental forces over billions of years. And then there's the radical possibility that some fields only activate under extreme conditions, like near black holes or in the searing heat of the early universe, effectively creating hidden layers of physics we've yet to uncover. What makes this especially fascinating is how these fields might interact. The Higgs could be entangled with undiscovered scalar fields in a cosmic dance, their combined effects explaining why the universe looks the way it does. Some models even propose that such interactions triggered phase transitions in the early cosmos moments when the very rules of reality changed abruptly, like water freezing into ice. These transitions might have generated gravitational waves we could detect with next-generation observatories, potentially opening a window into physics beyond anything our current theories can describe. The implications stretch beyond pure science. If additional scalar fields exist, they could rewrite our understanding of cosmic history. Maybe dark energy isn't constant but fluctuates due to an evolving field. Perhaps the universe's expansion will someday reverse because of a hidden field we haven't accounted for. Or maybe, just maybe, these fields hold clues to unifying quantum mechanics and gravity, revealing a deeper structure to reality where all forces emerge from a single, elegant framework. The Higgs was just the first whisper from this hidden world. The full conversation could change everything. One of the greatest mysteries in modern cosmology isn't just that the universe is expanding, it's that this expansion is speeding up against all expectations, as if space itself has an invisible foot pressing harder on the accelerator. For decades, scientists assumed this acceleration came from a static feature of the universe, Einstein's cosmological constant, a fixed energy density woven into the vacuum of space. But what if dark energy isn't constant at all? What if it's a dynamic, evolving field, one that ebbs and flows like tides in an unseen ocean? This is the tantalizing possibility behind quintessence theories, where dark energy isn't just background noise, but an active player in cosmic evolution. Imagine inflating a balloon at a steady pace, then suddenly feeling it stretch faster between your fingers for no apparent reason. That's essentially what astronomers observed in the late 1990s when distant supernova revealed the universe's expansion wasn't slowing down as predicted, it was accelerating. The simplest explanation, a cosmological constant, a uniform energy inherent to empty space. But there's a problem. When we calculate how strong this energy should be based on quantum theory, the numbers disagree by a factor of 10 to the power of 120. That's not just a rounding error, it's the worst mismatch in science. This cosmic coincidence problem suggests we might be missing something fundamental. Enter quintessence, a theoretical scalar field that could explain dark energy without relying on a fixed cosmological constant. Unlike a static energy, this field would change over time, sometimes strengthening, sometimes weakening. Picture a cosmic thermostat adjusting the universe's expansion rate dynamically. In some models, quintessence behaves like a fifth fundamental force, hence its name, from the ancient Greek term for fifth essence, interacting weakly with matter and stretching spacetime unevenly across cosmic history. Early in the universe, this field might have lain dormant while matter dominated. Later, as galaxies spread out and space grew emptier, the field could have awakened, pushing galaxies apart ever faster. The implications are profound. A dynamic dark energy field could mean the universe's fate isn't set in stone. Maybe the current acceleration is temporary, a cosmic phase that might reverse someday, leading to a big crunch. Or perhaps the field will grow stronger, tearing apart galaxies, stars, and eventually atoms in a big rip. Some versions even allow for regions where the field collapses, creating exotic bubbles with different physics within our universe. Unlike the rigid cosmological constant, quintessence offers a living, breathing alternative where dark energy has a rich inner life we're only beginning to decipher. Detecting this field's fingerprints isn't easy, but astronomers have clues. By measuring how dark energy's strength changes over billions of years, comparing ancient supernova, galaxy clustering, and the cosmic microwave background, we might catch quintessence in the act. Some experiments hunt for subtle variations in fundamental constants, which a dynamic field could influence. Others probe whether dark energy interacts with dark matter, creating cosmic feedback loops. And if the field oscillates, it might generate faint gravitational waves detectable by future observatories. What's striking is how quintessence bridges the very large and the very small. Such fields likely originated in the quantum chaos of the early universe, then grew to shape the cosmos on the grandest scales. If proven real, they'd show how deeply interconnected physics is, that the same phenomena governing subatomic particles might also steer the destiny of superclusters. This isn't just about solving a cosmological puzzle, it's about uncovering whether the universe's darkest secret is written in the language of hidden, ever-changing fields. Deep in the cosmic shadows, where ordinary matter refuses to glow, dark matter exerts its silent pull, bending light, sculpting galaxies, yet revealing nothing of its true nature. Among the most compelling candidates for this invisible cosmic architect is the axion, a hypothetical particle so ghostly it could pass through lead as effortlessly as light through glass. But don't let its elusive nature fool you. Axions might form vast, rippling fields stretching across the universe, their subtle vibrations generating the gravitational scaffolding that holds galaxies together. The axion story begins with a cosmic puzzle far smaller than galaxies, the mysterious symmetry of neutrons. In the 1970s, physicists noticed something peculiar. The strong nuclear force, which binds atomic nuclei, behaves with near-perfect symmetry despite quantum theory allowing for imbalances. To explain this, theorists proposed the existence of a new field that corrects this symmetry automatically, like an invisible hand tuning a cosmic instrument. The vibrations of this field would manifest as particles' actions so lightweight and weakly interacting that they'd barely leave a trace. Yet if they exist, their combined gravitational influence could account for dark matter's invisible grip on the cosmos. Detecting axions is like trying to catch whispers in a hurricane. These particles would rarely collide with normal matter, drifting through planets and detectors unnoticed. But where brute force fails, ingenuity steps in. Imagine turning the entire galaxy into a trap. Actions moving through magnetic fields, like those around neutron stars, might occasionally convert into faint photons, particles of light. Scientists have built ultra-sensitive detectors, chilled to near absolute zero, listening for these telltale flashes. Others exploit quantum tricks, using superconducting materials to amplify action's vanishingly weak signals into something measurable. The implications stretch far beyond dark matter. Action fields could solve multiple cosmic riddles at once. Some theories suggest these fields might have influenced the early universe's expansion, leaving fingerprints in the distribution of galaxies. Others propose actions as a bridge between quantum mechanics and gravity, their subtle interactions hinting at a deeper unity in physics. And if actions oscillate in specific patterns, they could even explain why the universe has so little antimatter, a bias written into the fabric of hidden fields. What makes this search thrilling is its sheer audacity. We're hunting for particles that might permeate every cubic inch of space, yet reveal themselves only under the most extraordinary conditions. Whether actions exist or not, the quest reshapes our understanding of reality's hidden layers, where the faintest tremors in unseen fields might hold the keys to the universe's darkest secrets. The universe didn't just begin, it exploded into existence with a sudden, staggering stretch, growing from smaller than an atom to the size of a grapefruit in a fraction of a second. This wasn't just fast expansion, it was a cosmic sprint, driven by a theoretical force so powerful it makes dark energy look sluggish. Enter the inflaton field, a hypothetical engine that might have powered this breathtaking phase of inflation, setting the stage for everything that followed. Picture a snowball rolling downhill, gathering mass and momentum until it's no longer just snow. It's an avalanche. The inflaton field could have worked similarly, trapped in a high-energy state after the Big Bang. As this field rolled toward a lower energy level, it released staggering amounts of energy, stretching space-time faster than light itself could keep up. This wasn't violation of physics. It was space-time itself expanding, carrying matter along for the ride. The result, a universe smoothed out like a crumpled sheet pulled taut, explaining why the cosmos looks so uniform in every direction we observe. But how do we know this isn't just a wild guess? The evidence is written in the oldest light we can see, the cosmic microwave background. This afterglow of the early universe isn't perfectly uniform. Tiny temperature fluctuations, hotter and colder patches no larger than 1 part in 100,000, form a cosmic fingerprint. These imperfections might be quantum ripples from the inflaton field itself, microscopic fluctuations stretched to cosmic scales during inflation. Imagine blowing up a balloon with tiny dots on its surface. As it expands, those dots grow into vast patterns. The universe did the same, magnifying quantum jitters into the seeds of galaxies. The inflaton field didn't just stretch space, it might have shaped time. Some models suggest inflation created a multiverse, where different regions of spacetime stopped inflating at different moments, each birthing a separate universe with its own physical laws. Our observable cosmos could be one bubble in an infinite froth of universes, each with its own unique inflaton story. This isn't just speculation. Certain signatures in the cosmic microwave background, like unusual patterns in polarization, might hint at collisions with other bubble universes, though no smoking gun has been found yet. What's fascinating is how inflation solves multiple cosmic puzzles at once. It explains why the universe is so flat, why distant regions have the same temperature despite never being in contact, and even why magnetic monopoles, theoretical relics from the early universe, are nowhere to be found. The inflaton field isn't just a placeholder for our ignorance. It's a framework that ties together disparate mysteries with startling elegance. Yet the story doesn't end there. If inflation happened, where did the inflaton field come from? Some theories link it to higher dimensional physics or grand unified theories, where it emerges naturally from the mathematics. Others speculate it might still exist in some residual form, lurking in the vacuum of space, its energy now dormant. Future experiments like ultra-precise measurements of the cosmic microwave background or observations of primordial gravitational waves could finally confirm whether this field is more than theory, whether it's the hidden architect of our reality. The inflattened field represents one of science's boldest ideas, a single mechanism that doesn't just explain how the universe began, but why it looks the way it does. If proven, it would mean that everything we see, galaxies, stars, even the fabric of space itself, was sculpted by vibrations in an invisible field during the universe's first fleeting moments. That's the power of hidden fields. They don't just fill the gaps in our knowledge, they rewrite the story of existence from the ground up. Some forces in the universe play hide and seek, changing their behavior depending on who's watching. Chameleon fields do exactly that, morphing their strength and range to blend into their surroundings like their namesake reptile. Imagine whispering in an empty room your voice carries clearly. But step into a crowded stadium and those same words vanish beneath the roar. Chameleon fields work similarly, growing faint in dense environments like Earth's atmosphere, yet surging in strength where matter is sparse, like the vast emptiness between galaxies. This adaptability might explain why we haven't detected them yet, even as they shape the cosmos in unseen ways. At their core, these fields represent a radical twist on gravity's rules. While Einstein's equations describe gravity as a constant force, chameleon theories suggest it could vary subtly based on surroundings. Picture a magnet's pull weakening when wrapped in thick cloth, except here, the cloth is the density of matter around the field. In places like our solar system, where planets and stars pack tightly together, the field suppresses its effects, staying hidden. But in the cosmic voids where galaxies float like lonely islands, the field stretches out unimpeded, possibly augmenting gravity just enough to explain dark matter's gravitational fingerprints without needing new particles. The implications are profound. If chameleon fields exist, they'd challenge our understanding of fundamental forces as fixed constants. Instead, gravity could become a flexible, context-dependent phenomenon. Some models suggest these fields might even explain the universe's accelerating expansion, acting like a cosmic dimmer switch that tweaks dark energy's strength based on location. This could solve the cosmic coincidence problem, why dark energy's effects became noticeable only after billions of years of cosmic evolution, by framing it not as luck, but as a natural consequence of an evolving field. Detecting something designed to evade detection requires clever workarounds. Scientists use ultra-precise torsion balances, devices that measure whispers of force between objects in vacuum chambers, to hunt for faint chameleon effects shielded from Earth's matter-heavy environment. Space-based experiments could be even more revealing, where the field's signal might amplify away from planetary interference. Others studied dense celestial objects like neutron stars, where extreme gravity could squeeze the field into observable behavior. What makes chameleon fields so compelling is their dual nature. They're not just another hidden variable, they redefine how forces interact with the universe's structure. If proven real, they'd show that the laws of physics aren't just written in stone, but adapt to their surroundings like living things. This isn't just about solving dark matter or dark energy. It's about uncovering whether the universe plays by different rules in different places, hiding its true face until we learn to look in just the right way. When two black holes collide, they don't just merge. They send ripples cascading through the fabric of spacetime itself. These gravitational waves, first detected by LIGO in 2015, aren't just cosmic echoes. They could be whispers from hidden tensor fields, structures woven into the universe's geometry that might hold clues to physics beyond Einstein. Picture spacetime not as a static stage, but as a dynamic, vibrating membrane where every massive event, like colliding neutron stars or black holes, tugs at its threads, sending oscillations racing outward at light speed. But what if these waves carry more information than we've realized? Tensor fields are mathematical objects that describe how quantities change across space and time, like arrows pointing in different directions at every point in space. In general relativity, the gravitational field itself is a tensor field, a complex, multidimensional entity that bends and stretches with matter and energy. But some theories suggest this might be just the visible tip of the iceberg. Additional tensor fields, invisible to us under normal circumstances, could interact subtly with gravity, modifying how gravitational waves propagate or how black holes ring down after collisions. LIGO observations already match Einstein's predictions with astonishing precision, but hidden tensor fields might leave tiny deviations, footprints in the data we're only now learning to read. Take dispersion, for example. In most media, waves slow down at different frequencies. Think of how light splits into colors through a prism. Gravitational waves shouldn't do this in pure general relativity. All frequencies should travel at the same speed. But if tensor fields couple to gravity, they might introduce minuscule dispersion effects, subtly altering high-frequency waves compared to low-frequency ones. Future detectors, like the space-based LISA observatory, could spot these anomalies by comparing waves from events billions of light-years apart. Another signature could be in the overtones, the harmonic frequencies black holes emit as they settle into their final form. Hidden fields might shift these tones in detectable ways, like an invisible hand plucking the strings of spacetime. The implications stretch beyond gravity. Some grand unified theories predict tensor fields that mediate interactions between known forces, potentially bridging quantum mechanics and relativity. Others suggest these fields could explain dark matter not as particles but as geometric structures embedded in spacetime. And in the most speculative models, tensor fields might even enable exotic phenomena like traversable wormholes, though these ideas remain firmly in the realm of hypothesis. What's certain is that gravitational waves have opened a new window on the cosmos, one where every ripple might carry secrets about the universe's hidden architecture. The next generation of detectors won't just listen for louder or more frequent waves, they'll tune into the finest details, hunting for clues that gravity isn't quite what we thought. Whether tensor fields exist or not, the search itself is refining our understanding of reality's deepest layers, proving that even the quietest signals from the cosmos can shake the foundations of physics. Even in complete darkness, at absolute zero temperature where all motion should cease, the universe still hums with restless energy. This is the zero-point field, a quantum phenomenon where empty space crackles with fleeting particles and electromagnetic waves popping in and out of existence. Unlike ordinary fields, this one never switches off. It's the background static of reality itself, a seething quantum foam where temporary particles borrow energy from the vacuum, existing just long enough to obey the uncertainty principle before vanishing again. The implications are staggering. What we perceive as nothing may actually be the most energetic state possible. The mathematics behind this is both beautiful and bewildering. Quantum field theory predicts that each cubic centimeter of empty space contains enough zero-point energy to boil all Earth's oceans, if we could somehow tap into it. The catch: this energy exists in a perfectly balanced state, like a cosmic checking account where deposits and withdrawals happen simultaneously. Measuring it directly is like trying to grasp smoke. The moment you reach out, the delicate balance collapses. Yet its effects are undeniable. The Casimir effect shows this vividly. Place two metal plates extremely close together in a vacuum, and the zero-point field pushes them together slightly, as if the universe itself is pressing in. Some theorists propose this field could explain dark energy's repulsive force stretching the cosmos apart. Others see potential technological revolutions. Imagine spacecraft propelled not by fuel, but by manipulating the vacuum's intrinsic energy. While mainstream physics remains skeptical of such applications, the underlying principle is sound. zero-point fluctuations generate real, measurable forces at microscopic scales. The challenge lies in scaling these effects to human-sized applications without violating conservation laws. Controversy swirls around the zero-point field's true nature. Some interpretations suggest it's merely a mathematical artifact, a useful calculation tool without physical reality. Alternative views propose it as a fundamental medium, a quantum ether connecting all points in space. Recent experiments with ultra-cold atoms and quantum optics hint at stranger possibilities like zero-point fluctuations influencing chemical reactions or even playing a role in quantum consciousness theories. What makes this field extraordinary is its dual role. It's both the foundation of quantum electrodynamics and one of physics' greatest unsolved puzzles. Whether it remains a theoretical curiosity or becomes the key to unlocking cosmic secrets, the zero-point field reminds us that the universe's deepest truths often hide in plain sight, woven into the fabric of what we mistakenly call emptiness. Gravity seems oddly feeble compared to nature's other forces. A fridge magnet can defy Earth's entire gravitational pull, yet electromagnetism barely notices. This cosmic imbalance has long puzzled physicists, but hidden dimensions might hold the answer. Imagine our universe as a three-dimensional sheet floating within a higher dimensional space called the bulk. While our familiar force is electromagnetism, the strong and weak nuclear forces are bound to this sheet. Gravity could be leaking into the extra dimensions, diluting its strength like water seeping through a sponge. This startling idea emerges from string theory, where up to 7 additional curled-up dimensions might exist beyond our perception. These extra dimensions aren't science fiction. They're mathematical necessities in theories attempting to unify quantum mechanics and gravity. The bulk's geometry could explain why gravity appears billions of times weaker than other forces. Picture a tuning fork vibrating in a room. The sound spreads in all directions, fading quickly. Similarly, gravity's influence might disperse into hidden dimensions, while other forces remain localized on our three-dimensional brain, short for membrane. This would mean we're only experiencing a fraction of gravity's true intensity, the rest vanishing into dimensions we can't access. Remarkably, this theory makes testable predictions. If gravity interacts with higher dimensions, its effect should deviate from Newton's inverse square law at extremely short distances. Experiments using exquisitely sensitive torsion balances have searched for such anomalies at scales smaller than a human hair. While no conclusive evidence has been found yet, future quantum gravity experiments might detect subtle fingerprints of these extra dimensions. Another clue could come from particle colliders. If enough energy is concentrated in one place, it might briefly create particles tied to these dimensions, appearing in our universe as sudden bursts of missing energy. The implications stretch beyond gravity's weakness. Bulk fields' vibrations propagating through these higher dimensions could mediate entirely new forces. Some models suggest dark matter might consist of particles moving freely through the bulk, rarely interacting with our brain except through gravity. Others propose that the Big Bang was triggered by a collision between brains floating in this higher dimensional space. Even more radically, these hidden dimensions might contain parallel versions of our own universe, separated by less than a millimeter along an unseen axis. What makes this theory so compelling is how it transforms our cosmic perspective. The universe might be vastly larger and more interconnected than we perceive, not just in space, but in dimensions we can't see or touch. Every gravitational wave, every falling apple could carry whispers from these hidden realms, hinting at a reality far grander than our senses reveal. Whether these dimensions exist remains uncertain, but their mathematical elegance keeps drawing physicists deeper into the bulk, or where the answers to gravity's greatest mysteries might be hiding in plain sight, just beyond our dimensional horizon. What if memory isn't stored in your brain, but in the very fabric of the universe? Rupert Sheldrake's morphic field hypothesis proposes exactly this: a radical vision where hidden fields act as cosmic blueprints, shaping everything from crystal formation to animal behavior. Unlike conventional physics, which sees fields as passive scaffolds, Sheldrake imagines them as living repositories of collective memory, evolving alongside the systems they influence. Picture a flock of birds wheeling in perfect synchrony without a leader, not because of instinct alone, but because each bird taps into an invisible field of shared flight patterns accumulated over generations. This isn't just poetic speculation, it's a testable, if contentious, scientific proposition. The theory hinges on formative causation, the idea that patterns become easier to replicate the more they recur. Sheldrake compares it to tuning a radio. The first time a molecule crystallizes or a rat learns a maze, it broadcasts that pattern into a morphic field. Subsequent attempts then tune into this field, making the process faster or more likely. In one provocative experiment, he suggested that if laboratory rats worldwide learned a maze faster over time, even control groups with no trained ancestors might show accelerated learning, as if the morphic field had been charged by collective experience. While mainstream biology remains skeptical, citing insufficient evidence, the implications are staggering. Could human language, cultural traditions, even instincts be shaped by similar fields? Critics argue morphic fields violate known physical laws, lacking detectable energy or mechanistic explanations. Yet Sheldrake counters that gravitational fields were once equally mysterious, invisible influences accepted long before their quantum carrier, the graviton, was hypothesized. He points to unexplained phenomena like termites simultaneously altering nest architecture across continents, or how new chemical compounds suddenly crystallize more readily worldwide after their first synthesis. These anomalies, he claims, hint at a universe where habits harden into physical laws through repetition, a cosmos that learns from itself. The hypothesis also challenges Darwinism's randomness by proposing an additional evolutionary mechanism, not just mutation and selection, but the gravitational pull of successful forms. Imagine a sculptor shaping clay, except the clay itself remembers past shapes and resists deviation. In this view, DNA doesn't carry all hereditary information. Morphic fields supplement the genetic code, guiding embryos to develop similarly to ancestors without explicit instructions. Some researchers even speculate these fields could explain phantom limb sensations. The persistent presence of amputated arms or legs might reflect lingering morphic patterns awaiting update. Beyond biology, the theory dares to reinterpret physics itself. Sheldrake suggests that so-called constants of nature, like the speed of light, might be habits rather than fixed laws subtly evolving as the universe ages. This echoes astronomer Lee Smollen's idea of cosmological natural selection, where universes learn optimal parameters over cosmic time. If true, our most cherished scientific truths might be deeper habits inscribed in hidden fields subject to gradual change. Whether morphic fields exist or not, the hypothesis forces a profound question. Could reality have a memory, not as metaphor but as physics? An active, participatory process where the past literally shapes the present. In a universe teeming with dark matter, quantum entanglement, and elusive dark energy, perhaps the boldest idea isn't that such fields exist, but that we've overlooked them for so long. Einstein's universe has a speed limit. Nothing travels faster than light. But what if there's a cosmic loophole hidden in the geometry of space-time itself? Torsion fields propose exactly that, suggesting that twisting the fabric of reality might unlock phenomena even relativity can't explain. Unlike gravity, which warps space-time like a bowling ball on a mattress, torsion arises from rotation. Imagine drilling into that mattress, creating spiraling indentations that could, in theory, carry information or energy in ways straight-line gravity never could. This isn't just abstract math. Some physicists believe torsion could explain everything from dark matter's behavior to the possibility of faster-than-light communication. The roots of this idea stretch back to the early 20th century, when mathematicians first explored geometries where spacetime doesn't just bend, it twists. In these models, every rotating object, from electrons to galaxies, generates a subtle torsion field like a cosmic whirlpool. While mainstream relativity ignores these effects, alternative theories like Einstein-Cartan science embrace them, proposing that spinning matter could twist spacetime's structure at microscopic scales. The implications are staggering. If particles exchange information through these spiraling geometries, they might bypass light speed's restrictions, not by breaking physics, but by taking a hidden shortcut through spacetime's coiled underbelly. One daring application: propulsion. Torsion fields could theoretically allow spacecraft to surf rotating spacetime geometries without traditional fuel. Think of it as cosmic telekinesis, where precisely spun masses manipulate local gravity. Russian scientist Nikolai Kozyrev experimented with this in the mid-20th century, claiming gyroscopes in vacuum chambers exhibited anomalous forces when spun at high velocities. Though dismissed by mainstream science, his work inspired later research into inertial mass reduction, the idea that rapidly rotating objects might shield or redirect gravity's pull. Even NASA EagleWorks Lab has explored torsion-based propulsion concepts, albeit with inconclusive results, but the wildest possibility lies in communication. If torsion waves propagate instantaneously across the universe, as some theories suggest, they could solve quantum entanglements, spooky action at a distance, not as magic, but as spacetime's hidden spin dynamics at work. Picture two entangled particles as corks floating on opposite ends of a twisting river. Their instantaneous connection isn't through space, but through the unseen currents beneath. Experiments with rotating superconductors have hinted at anomalous energy transfers that torsion might explain, though the data remains hotly debated. Critics argue torsion fields lack empirical evidence, existing primarily as elegant equations. Yet proponents counter that dark matter's gravitational effects, especially in galaxies with counterintuitive rotation curves, align eerily well with torsion-based predictions. Maybe what we call dark matter is just spacetime's twisted geometry manifesting on cosmic scales. The truth might lie in the middle. Torsion could be one thread in a larger tapestry of hidden fields, its effects too subtle for current instruments but revolutionary if proven. What makes torsion thrilling is its defiance of conventional limits. In a universe where black holes spin at nearly light speed and quantum particles exhibit intrinsic angular momentum, why wouldn't spacetime itself have a rotational dimension we've yet to fully grasp? Whether it enables star drives or merely deepens our understanding of spin's cosmic role, torsion reminds us that reality's rulebook might have chapters we're only beginning to decipher, written not in straight lines but in spirals. Imagine if every particle, every planet, every thought in the universe wasn't just made of matter or energy, but of information, not as a metaphor, but as a literal physical field woven into the fabric of spacetime. This is the radical premise of the information field theory, where reality itself might function like a cosmic hard drive with bits and bytes as fundamental as atoms. At its core, this idea suggests that the universe isn't just described by information. It might be information operating under rules we're only beginning to decode. The roots of this theory stretch back to the holographic principle, born from black hole physics. When scientists realized the information content of a black hole scales with its surface area rather than its volume, it hinted at something extraordinary. That all the data describing a three-dimensional space could somehow be encoded on a two-dimensional boundary, like a cosmic projector screen. Take a hologram, shine light on a flat surface, and a three-dimensional image appears. Similarly, our universe's richness, stars, galaxies, consciousness, might be a hologram emerging from information imprinted on spacetime's edge. If true, it would mean what we perceive as depth, solidity, even time, could be illusions generated by an underlying informational architecture. Quantum entanglement adds another layer of intrigue. When particles become entangled, measuring one instantly affects its partner, no matter the distance. Einstein called this spooky action at a distance, but information field theory offers a possible explanation. Entangled particles aren't communicating faster than light. They're accessing a deeper layer of reality where their connection is written into the universe's informational substrate. Picture two computers linked to the same cloud server. Changes on one appear instantly on the other, not because data travels between them, but because both draw from a shared source. Similarly, entangled particles might be terminals plugged into the cosmos's hidden information field. This idea reaches its most provocative form in the it-from-bit hypothesis, coined by physicist John Archibald Wheeler. He proposed that every particle, every force, even spacetime itself, derives from binary, yes, no questions cosmic bits flickering into existence like pixels on a screen. In this view, the universe isn't a machine made of gears and cogs, but a computation unfolding according to informational rules. The implications are staggering. Black holes might be nature's ultimate data compressors. The Big Bang could have been an informational phase transition, and consciousness itself might be a process of interacting with this fundamental field. Critics argue that without a mechanism to explain how information manifests as physical reality, the theory remains speculative, yet experiments are probing its edges. Scientists have used quantum computers to simulate holographic universes, finding eerie parallels between quantum circuits and spacetime geometry. Others study how entanglement entropy, a measure of quantum information, mirrors the equations describing black holes. Even the James Webb Space Telescope's deep field images, revealing universe-scale structures, might hold clues about how information organizes cosmic architecture. Whether this theory holds or not, it reframes our place in the cosmos. If information is fundamental, then every observation, every measurement becomes a kind of cosmic dialogue with the universe's deepest layer. We're not just passive inhabitants of reality, we're participants in its ongoing computation, where every thought and action might ripple through the information field in ways we're only beginning to imagine. The 19th century's greatest scientific ghost wasn't a particle or a force, it was the luminiferous ether, an invisible medium thought to carry light waves across the emptiness of space. Dismissed after Einstein's relativity showed light needed no such medium, the ether became a cautionary tale about dead-end theories. But what if we buried it too soon? Modern quantum field theory paints a startling picture of empty space, not as true emptiness, but as a seething quantum foam full of temporary particles and fluctuating energies. In this light, the old ether concept starts to look less like a mistake and more like an intuition ahead of its time. Think of the original ether as a cosmic ocean, a static, undetectable fluid through which light rippled like waves. When Michelson and Morley failed to measure Earth's motion through this supposed medium in 1887, it seemed proof the ether didn't exist. Yet today's quantum vacuum is strangely reminiscent of that discarded idea. Space isn't empty, it crackles with virtual particles that borrow energy to briefly exist, governed by quantum fields that permeate every inch of the universe. These fields aren't just mathematical tools, they're real, measurable entities that can vibrate, interact, and even curve spacetime itself. In essence, we've resurrected the ether not as a physical substance, but as a dynamic, energetic substrate underlying reality. The parallels go deeper. Just as the old ether was thought to give light its wave nature, quantum fields like the electromagnetic field are literally what light waves ripple through. The difference: these fields aren't absolute or motionless like the classical ether, they're local and relativistic, bending to Einstein's rules. But the core idea remains: light doesn't travel through nothing. It propagates through something, a quantum field that, in many ways, fulfills the ether's original role without violating relativity. Even the famous Higgs field, which gives particles mass, behaves like a modern cousin of the ether, filling space and interacting universally with matter. Where the old model truly failed was in its rigidity. 19th century physicists imagined the ether as a fixed reference frame, a universal backdrop against which all motion could be measured. Relativity shattered that notion, showing space and time are relative to the observer. Yet quantum field theory offers a compromise: fields that exist everywhere, but whose effects depend entirely on local conditions. It's as if the ether wasn't wrong, just incomplete. The universe does have a pervasive medium, it's just far more flexible and mind-bending than anyone initially suspected. Perhaps the most tantalizing twist comes from dark energy. If empty space contains intrinsic energy, as quantum theory suggests, could this be the ether's final revenge? The cosmological constant, Einstein's greatest blunder, was reintroduced to explain dark energy's push on the expanding cosmos. But what if this constant isn't just a number in an equation? What if it's the energy of space itself, a modern ether subtly shaping the universe's fate? The equations bear an uncanny resemblance. Both concepts assign properties to the void. Only now we have the math to back it up. This isn't to say the old ether theorists were right all along. Their model lacked the sophistication to describe relativity or quantum effects. But their instinct that space isn't truly empty turns out to be profound. Science often progresses not by discarding old ideas entirely, but by refining them into something more nuanced. The ether may have been banished from textbooks, but in the quantum fields humming through the cosmos, its spirit lives on, not as a failed hypothesis, but as a stepping stone to deeper truths. After all, sometimes the most discredited ideas just need the right lens to be seen anew. Time crystals sound like something straight out of science fiction, structures that repeat not in space, but in time, defying our usual expectations of how matter behaves. Unlike ordinary crystals, where atoms arrange in regular spatial patterns like a grid, time crystals exhibit patterns that cycle periodically without any energy input, essentially breaking time symmetry. Picture a clock that ticks forever without winding, or a dance that repeats endlessly without the dancers ever tiring. This bizarre phenomenon, first theorized by Nobel laureate Frank Wilczek in 2012, was initially met with skepticism. How could something oscillate perpetually without violating the laws of thermodynamics? Yet by 2017, researchers had created time crystals in the lab using chains of ions or defects in diamonds, proving these strange structures are very real. The secret lies in hidden temporal fields, underlying patterns in quantum systems that lock particles into rhythmic motion. Think of a metronome that keeps perfect time not because it's powered, but because it's synchronized to an invisible beat woven into the fabric of reality. In time crystals, this beat emerges from quantum interactions that force particles to flip states at fixed intervals, even in their lowest energy state. It's as if the universe has a silent drummer, keeping time for these structures long after external forces fade away. Unlike anything else in physics, time crystals don't settle into equilibrium. They perpetually dance between states, making them the first known examples of non-equilibrium matter. What makes this truly mind-bending is the implication for time itself. Normally, the laws of physics don't care about the direction of time. A film of atomic interactions played forward or backward looks equally valid. But time crystals break this symmetry, creating an arrow of time at the microscopic level. Some theorists speculate these structures might be glimpses of deeper temporal fields, hidden rhythms that could influence everything from quantum computing to cosmology. Imagine a universe where time isn't just a backdrop but an active participant with layers of oscillation we're only beginning to detect. Practical applications are already emerging. Time crystals could revolutionize precision sensors or serve as fault-resistant qubits in quantum computers, their stable oscillations providing perfect timing references. More radically, their existence hints at undiscovered phases of matter where time, not just space, holds the key to organization. And if temporal fields exist beyond the lab, might they play a role in cosmic phenomena? Could pulsars, those celestial lighthouses with freakishly regular beats, be nature's own time crystals on a stellar scale? The most tantalizing possibility is that time crystals bridge the microscopic and cosmic. If space-time itself has granular structure at quantum scales, as some theories suggest, these temporal patterns might be the stitches holding it together. We're left with a profound question. What if time isn't what we think it is, not a featureless river but a layered symphony of hidden rhythms, and time crystals are our first hint of the score? Einstein spent the last 30 years of his life chasing a dream, a single equation that would unite all the forces of nature under one grand framework. To him, the universe's splintered forces, gravity, electromagnetism, the strong and weak nuclear interactions, were like instruments playing out of tune, waiting for a conductor to harmonize them into one symphony. This wasn't just academic curiosity, it was a conviction that reality, at its core, must be elegantly simple. His quest for a unified field theory consumed him, but the tools of his era weren't enough to crack the code. Today, that dream lives on in theories so ambitious they make relativity seem like child's play. Take quantum gravity, for instance. General relativity describes gravity as the curvature of space-time, while quantum mechanics paints particles as probabilistic waves. The problem: these frameworks speak entirely different languages, one deterministic and smooth, the other chaotic and pixelated. Imagine trying to merge a classical orchestra with a jazz improvisation. The rhythms clash, the scales disagree. That's the challenge physicists face when they attempt to quantize gravity. Some theories, like loop quantum gravity, suggest space-time itself might be woven from tiny, discrete loops. Think of a cosmic tapestry where each thread is a vibrating strand of reality. Others propose that gravity emerges from quantum entanglement, with particles linking across space in a hidden web of connections. Then there's string theory, the most audacious contender in the unification game. It reimagines particles not as dots but as vibrating strings, each oscillation mode producing a different particle, like guitar strings playing the notes of the universe. The catch: these strings dance in 10 or 11 dimensions, 6 or 7 of them curled up smaller than atoms. In this view, the forces we know might just be different vibrations of the same underlying strings, much like how light and radio waves are both oscillations of the electromagnetic field. String theory's most tantalizing offshoot, M-theory, even posits that our universe floats on a membrane in a higher dimensional space, with gravity leaking in from adjacent dimensions. But unification isn't just about equations, it's about reshaping how we see reality. If successful, these theories could reveal that black holes and atoms, galaxies and quarks, are all facets of one unified field, like ice, water, and steam are phases of H2O. Dark energy might be the hum of a field we've yet to detect, and the Big Bang could be a phase transition in this cosmic medium, like steam condensing into droplets. The implications stretch beyond physics. They'd redefine what it means to exist in a universe where all forces, all matter, are threads of the same fabric. Critics argue these theories are untestable, their mathematics too abstract, yet experiments are inching closer. Gravitational wave detectors might uncover deviations from Einstein's predictions, hinting at quantum gravity's fingerprints. Particle colliders could produce micro-black holes or extra-dimensional effects if the energy is high enough, and cosmic surveys might find patterns in the universe's structure that only string theory can explain. The dream of unification isn't dead. It's evolving, pushing us to imagine a reality far stranger and far more connected than Einstein ever dared to dream. Every living cell in your body might be quietly glowing not with metaphorical radiance, but with actual photons of light. This isn't science fiction. It's the startling premise of biophotonics, the study of ultraweak light emissions from biological systems. Discovered in the 1920s by Russian scientist Alexander Gurevich, who noticed onion roots seemed to communicate growth patterns via light. These faint glimmers are now measurable with supersensitive photomultiplier tubes. We're talking about light so dim it's 1 billion times weaker than candlelight, but if every cell emits just a few photons, their collective glow could form a subtle luminous field around every living thing. What if this light isn't just a byproduct but a hidden language of life itself? The mechanics behind biophotons are as fascinating as they are mysterious. Most originate from metabolic reactions, particularly when free radicals interact with molecules in cells, releasing energy as light, a process called chemiluminescence. But here's where it gets weird. These emissions aren't random noise. Studies show they follow rhythmic patterns, syncing with circadian cycles and even correlating with stress or disease states. Cancer cells, for instance, emit chaotic photon bursts compared to healthy cells' orderly signals. Some researchers speculate this could be nature's way of enabling cellular communication, like a biological Wi-Fi where information is transmitted not chemically but optically. Imagine your body's trillions of cells constantly whispering to each other in flashes of light, coordinating repairs, immune responses, or even consciousness. The boldest theories suggest biophoton fields might extend beyond mere biochemistry. Quantum biologist Fritz Albert Popp proposed that these light emissions could form a coherent field, a laser-like network where photons become entangled, creating a unified quantum state across an organism. In this view, your brain isn't just an electrical computer. It's a light-based processor where consciousness arises from synchronized biophoton patterns. Experiments with algae and plants show they transfer light information between leaves faster than chemical signals could travel, hinting at non-local communication channels. If true, this could explain phenomena like placebo effects or acupuncture, where invisible energy pathways might really be biophoton networks we're just beginning to map. Skeptics argue these ideas veer into pseudoscience, citing the extreme faintness of biophoton signals. Yet recent breakthroughs give the field new credibility. Scientists using quantum optics have detected photon entanglement in photosynthesis, proving nature harnesses quantum effects in light harvesting. Others have filmed real-time biophoton streams around human hands using cryogenic cameras, revealing pulsing geometries that change with meditation or intention. Even conventional medicine acknowledges light's role in healing. Phototherapy accelerates wound repair, while low-level laser treatments reduce inflammation. The line between mysticism and biophysics blurs when living systems demonstrably interact with light in ways we're only starting to decode. What makes biophoton fields so compelling is their potential to bridge the gap between material and energetic views of life. Ancient traditions spoke of luminous auras long before microscopes existed. Modern physics now suggests they might have been onto something, not as supernatural phenomena, but as measurable quantum biological processes. Whether these fields influence health, consciousness, or even interpersonal connections remains hotly debated. But one thing's certain: if cells truly communicate through light, we're standing at the threshold of a radical new understanding of life's hidden architecture, where the glow of a single cell might illuminate mysteries as vast as the mind itself. The cosmic microwave background is often called the universe's baby picture, a snapshot of the cosmos when it was just 380,000 years old. But this ancient light holds strange wrinkles that shouldn't be there. Like a photograph with faint, unexplained shadows in the corners, the CMB shows anomalies that defy standard cosmology's predictions. One of the most baffling is the axis of evil, a mysterious alignment of hot and cold spots stretching across the sky in a pattern that seems to point toward a specific cosmic direction. If the Big Bang was truly random, such structure shouldn't exist. It's as if the early universe had a preferred orientation, a hidden arrow scribbled into the fabric of space-time itself. These irregularities might be more than statistical flukes. Some theorists propose their scars from primordial field structures woven into the universe's infancy that left imprints as space-time stretched during inflation. Picture a loaf of bread baking with raisins inside. As the dough expands, the raisins move apart, but any initial clusters or patterns in their arrangement remain visible. Similarly, primordial fields could have created density variations that inflation magnified into the anomalies we see today. One leading candidate is the Curvaton field, a hypothetical scalar field that could have interacted with inflation's energy, seeding the CMB's odd asymmetries. Another possibility involves vector fields, unlike scalar fields that have magnitude but no direction. These would have introduced preferred axes in the early universe, potentially explaining the axis of evil's eerie alignment. The evidence isn't just visual. Precise measurements of the CMB's polarization, the way its light waves vibrate, reveal unexpected swirls known as B modes. While some B modes come from gravitational waves, others might trace back to primordial magnetic fields, another form of hidden influence from the universe's first moments. Imagine the early cosmos as a turbulent plasma, crisscrossed with currents of charged particles generating magnetic fields. Even if those original fields faded, their descendants could linger, subtly twisting the CMB's light over billions of years. Experiments like the upcoming Light-Bird satellite aim to tease apart these signals, searching for the fingerprints of fields that might have shaped reality before the first stars even flickered to life. The stakes couldn't be higher. If primordial fields are real, they'd rewrite our understanding of cosmic dawn. The so-called statistical anomalies might actually be cosmic breadcrumbs, leading us to a deeper layer of physics operating at energies far beyond what particle colliders can reach. It's like discovering a fossilized footprint that suggests dinosaurs didn't just walk, they danced. The CMB's imperfections could be our only window into an era when the universe was a trillionth of a second old. A time when hidden fields might have dictated everything from the distribution of galaxies to the very arrows of time and entropy. Detecting these signals requires instruments of breathtaking sensitivity. Telescopes at the South Pole and high-altitude balloons scan the sky, isolating the CMB's whispers from the cacophony of galactic noise. Each new data release brings fresh puzzles, cold spots too large to explain, correlations between distant points that shouldn't know about each other under standard physics. The most radical interpretation: these aren't anomalies at all, they're evidence of a pre-Big Bang phase, a cosmic memory imprinted by cycles of universes before ours. Whether the truth lies in exotic fields, higher dimensions, or something entirely unimagined, one thing is clear: the CMB isn't just a relic, it's a cipher, and we're only beginning to crack its code. Dark energy already stretches the cosmos like an invisible hand, but phantom energy is its terrifying cousin, a hypothetical field that wouldn't just accelerate the universe's expansion, but could eventually shred space-time itself. Picture blowing up a balloon, but instead of stopping when it's full, you keep pumping air until the rubber stretches too thin, quivers, then pops violently. That's the essence of the Big Rip, a doomsday scenario where phantom energy's repulsive force grows infinitely stronger over time, overwhelming gravity, then atomic forces, until every star, planet, and molecule is torn apart from within. Unlike ordinary dark energy, which remains constant or weakens gradually, phantom energy is defined by its equation of state, a value called W that's less than -1. This tiny mathematical quirk makes all the difference. Normal dark energy pushes galaxies apart gently, like a steady breeze. Phantom energy behaves more like a hurricane gaining strength, amplifying its own effects as space expands. In some models, this feedback loop means the universe wouldn't just fade into cold emptiness, it would face a violent, catastrophic end where even the fabric of reality ruptures. The timeline is what chills cosmologists. If phantom energy exists, the countdown could start surprisingly soon, cosmologically speaking. Within tens of billions of years, galaxies beyond our local group would vanish over the cosmic horizon, redshifted into oblivion. Later, the Milky Way would dissolve as phantom energy overpowers its gravity. In the final months, stars would flare and explode as their nuclear bonds fail. Planets would disintegrate hours before the end. In the last unimaginable instance, atoms themselves would be ripped apart, followed by spacetime's fundamental structure fragmenting into nothingness. Yet the wildest implication isn't destruction, it's observation. If phantom energy's influence is already growing, its fingerprints might hide in subtle changes in dark energy's strength over cosmic time. Astronomers hunt for these clues by comparing ancient supernovae with recent ones, measuring whether the universe's expansion accelerates faster now than billions of years ago. Other experiments probe the clustering of galaxies' phantom energy would leave a distinct signature, suppressing the formation of large-scale structures earlier than expected. Even gravitational wave detectors could spot anomalies if phantom energy alters how spacetime ripples propagate across billions of light-years. Skeptics argue phantom energy violates energy conditions fundamental to general relativity, potentially leading to paradoxes like negative energy densities or causality violations. But others counter that quantum field theory allows for such exotic states under extreme conditions. After all, the inflationary epoch which stretched the universe exponentially in its first moments required similar repulsive gravity. Phantom energy might be inflation's dark twin, a late universe resurgence of that same explosive potential. What makes this theory so haunting is its duality. It's both a prediction and a warning. If the universe contains even a trace of phantom energy, no matter how faint, it could spell an inevitable demise far more dramatic than heat death or collapse. Yet it also reminds us how fragile reality's framework might be, balanced on equations we've only begun to understand. Whether this field is real or not, its possibility stretches our imagination to cosmic limits where the end isn't just silence, but a scream written into the mathematics of the void. Magnets as we know them always come in pairs, a north pole inseparable from its south. Break a magnet in half and you don't isolate a single pole, you just create two smaller dipoles. This symmetry is so fundamental that James Clerk Maxwell baked it into his famous equations of electromagnetism in the 1800s. But what if nature has a secret? What if particles carrying just one magnetic pole, north or south, but never both, are lurking undiscovered, their existence rewriting physics as we know it? These hypothetical particles, called magnetic monopoles, aren't just curiosities. If they exist, they'd imply an entirely new kind of field woven into the universe's fabric, one that could reshape everything from quantum theory to cosmic evolution. The hunt for monopoles began in earnest when physicist Paul Dirac demonstrated something startling in 1931. Their existence would perfectly explain why electric charge comes in discrete, quantized units. His math suggested that even a single monopole in the universe would force charges to be multiples of a fundamental value, a breathtaking connection between magnetism and quantum mechanics. Imagine a cosmic lock and key where the mere presence of monopoles dictates the rules of electromagnetism for all particles. Dirac's work implied that if monopoles exist, they'd be extraordinarily massive, perhaps as heavy as a bacterium compressed into a single particle, making them relics of the early universe's highest energies. But the implications go deeper. Monopoles wouldn't just tweak Maxwell's equations, they'd revolutionize them. Traditional electromagnetism treats electric and magnetic fields as mirror images, but with crucial differences. Electric charges exist while magnetic charges don't. Introduce monopoles and this asymmetry collapses. Suddenly, magnetism gets its own version of electric charge, and the equations gain a stunning symmetry. This isn't just aesthetic, it could solve lingering mysteries like why the universe seems to prefer matter over antimatter. Some grand unified theories predict that monopoles were copiously produced in the searing heat of the Big Bang, their interactions potentially tipping the scales toward matter's dominance. The cosmic consequences are even wilder. If monopoles were forged in the early universe, their sheer density could have altered its expansion rate or even triggered phase transitions in spacetime structure. Inflation. The universe's rapid early growth might have been nature's way of diluting monopoles to near undetectable levels, solving the monopole problem that plagued early cosmology. Yet some theories suggest a few could have survived, lurking in the vast voids between galaxies or trapped inside dense celestial objects like neutron stars. Their magnetic fields, billions of times stronger than Earth's, might leave detectable imprints on passing cosmic rays or distort the light of distant quasars. Detecting these elusive particles is like searching for cosmic needles in a universe-sized haystack. Experiments range from ancient Antarctic ice cores, where monopoles could leave trails of atomic disruption, to superconducting loops designed to catch their fleeting magnetic signals. The most creative approaches involve repurposing Earth itself as a detector. As monopoles pass through the planet's magnetic field, they might generate faint radio pulses detectable by arrays of antennas. Even with decades of searching, no confirmed monopole has been found, but absence of evidence isn't evidence of absence. Their rarity or weak interactions might simply mean we haven't built the right trap yet. The most tantalizing possibility, monopoles might not be mere particles, but carriers of a hidden field that permeates the cosmos. Just as electric charges create electric fields, a sea of monopoles could generate a sprawling magnetic field on scales we've never imagined, one that subtly influences galactic rotation or dark matter's distribution. In this view, the monopole isn't just a missing piece of physics. It's a portal to a deeper layer of reality, where magnetism's full symmetry is restored, and the universe's hidden order finally comes into view. Whether they're awaiting discovery or destined to remain theoretical ghosts, magnetic monopoles remind us that the simplest questions like why magnets always have two poles can lead to the most profound revolutions. What if consciousness isn't just a byproduct of the brain, but a fundamental force woven into the universe itself, a noetic field that interacts with matter on the deepest levels? This radical idea, explored by pioneers like biologist Rupert Sheldrake and physicist Erwin Laszlo, suggests that subjective experience isn't confined to skulls and synapses. Instead, it might be a pervasive feature of reality like gravity or electromagnetism, resonating through the fabric of space-time in ways science is only beginning to grasp. Take quantum mechanics' infamous measurement problem. When particles exist as probability waves until observed, what exactly counts as an observer? Traditional interpretations stumble here, but a noetic field offers a startling alternative. Consciousness itself could collapse the wave function, not as a passive witness, but as an active participant in reality's unfolding. Experiments in quantum biology add fuel to this fire. Photosynthesis relies on near-instantaneous energy transfers that classical physics can't explain unless quantum coherence plays a role. If plants harness quantum effects to optimize sunlight absorption, could consciousness itself be leveraging similar phenomena at a grander scale? The implications ripple outward. Near-death experiences often defy materialist explanations, with patients recalling verifiable details during clinical death. Shared intentionality studies show synchronized brainwaves between meditators separated by miles, as if minds tune into a common field. Even placebo effects hint at something deeper. When belief alone heals, is it tapping into a noetic framework where expectation shapes physical outcomes? These aren't just anomalies, they're potential fingerprints of a consciousness field interacting with matter. Critics argue this veers into pseudoscience, lacking rigorous mathematical frameworks. Yet the gap is narrowing. Integrated information theory models consciousness as a property of any system with sufficient complexity, from brains to advanced AI. Or theory, proposed by physicist Sir Roger Penrose and anesthesiologist Stuart Hameroff, suggests quantum vibrations in microtubules, tiny structures inside neurons, could bridge mind and quantum physics. Meanwhile, lab experiments with entangled photons demonstrate that observation alters their states instantaneously, even across vast distances, a phenomenon that aligns eerily with noetic field predictions. What makes this theory so compelling is its unifying potential. If consciousness is indeed a fundamental field, it could explain everything from intuition's uncanny accuracy to the collective creativity underpinning human progress. Imagine artistic inspiration not as neural firings, but as temporary alignments with a broader noetic current, ideas literally in the air waiting to be received. Ancient traditions spoke of the Akashic records or the collective unconscious. Modern physics might be rediscovering these concepts through the lens of quantum fields. The noetic field hypothesis doesn't just challenge our understanding of mind, it redefines our place in the cosmos. We're not isolated observers peering at reality from afar. We're dynamic nodes in a vast, conscious network, shaping and shaped by a universe more alive, more interconnected than we ever dared to dream. Whether this field exists remains unproven, but the quest to find it is already transforming science, and perhaps in time, our very sense of what it means to exist. The universe as we know it might be stuck in an endless loop of cosmic destruction and rebirth, not through a singular Big Bang, but through colossal collisions between shimmering membranes floating in a higher dimensional space. This is the heart of the ekpyrotic field theory, a breathtaking alternative to inflation where our entire cosmos exists on a three-dimensional brain drifting through an unseen realm. Picture two sheets of paper floating parallel in a dark room, each representing an entire universe. When they drift too close, they collide with unimaginable energy, sparking a new cycle of cosmic evolution, like a cosmic reset button pressed at intervals spanning trillions of years. At the center of this cycle lies the ekpyrotic field, a hidden scalar field governing the brain's slow attraction and violent separation. Unlike the inflattened field that drove rapid expansion, this field operates in stealth mode, quietly building potential energy as the brains draw nearer over eons. When they finally collide, that stored energy explodes into heat and matter, mimicking the conditions of a Big Bang while avoiding the infinities that plague classical singularity models. The aftermath isn't chaos, though, because the field's oscillations fine-tune the collision's angles and energies. The newborn universe inherits the same finely balanced constants we observe today, from the strength of gravity to the mass of electrons. The elegance of this model lies in its problem-solving. Where inflation struggles to explain the universe's improbable flatness and uniformity, the ekpyrotic scenario naturally smooths things out through repeated cycles, each collision ironing out wrinkles from the previous iteration. Even dark energy finds a fresh interpretation, not as a mysterious repulsive force, but as a symptom of the brain's increasing separation, stretching space-time as they prepare for the next encounter. And here's the wildest twist: if brains can collide once, why couldn't there be layers of them, sparking countless parallel universes with every impact? Evidence for this radical vision might hide in gravitational waves. While inflation predicts a primordial gravitational wave background with specific signatures, ekpyrosis leaves a distinct fingerprint: suppressed low-frequency waves but potential high-frequency bursts from brain collisions. Future detectors like the Big Bang Observer could sift through the cosmic static for these telltale signals, Others hunt for anomalies in the cosmic microwave background's polarization patterns that might bear scars from pre-Big Bang interactions. Critics argue the theory relies too heavily on unobserved higher dimensions and lacks inflation's predictive precision. But supporters counter that it solves long-standing puzzles, like why entropy didn't start at maximum, each cycle begins fresh, and how quantum fluctuations could seed galaxies without invoking untestable multiverses. The ekpyrotic field isn't just another cosmological model. It's a bridge between string theory's abstract landscape and the tangible universe we inhabit, suggesting our reality might be one page in an infinite cosmic flipbook, rewritten with every collision. What makes this idea so compelling is its cyclical grandeur. Instead of a one-time creation event, we're part of an eternal rhythm where universes breathe in and out like living things. Time itself becomes a spiral rather than a line, each iteration subtly different, yet bound by the same underlying physics. Whether the ekpyrotic field is real or not, it expands our imagination of what's possible, revealing a cosmos far stranger and far more resilient than we ever dared to dream. What if dark energy isn't just one thing? What if it's two forces locked in an eternal tug of war, one pulling the universe toward expansion, the other toward annihilation? The quantum field theory proposes exactly that, a hybrid of quintessence and phantom energy, blending their opposite behaviors into a single, dynamic field that could explain dark energy's most baffling quirks. Picture a cosmic seesaw where the weight shifts over time, sometimes lifting the universe toward gentle growth, other times slamming it toward a violent end. At its core, the quantum field is a mathematical tightrope walk. Quintessence, as we've seen, is a scalar field that gently adjusts dark energy's strength over time, like a thermostat fine-tuning the universe's expansion. Phantom energy, on the other hand, is the universe's self-destruct button, a field whose repulsive force grows infinitely stronger, threatening to rip spacetime apart in a big rip. The quantum model marries these extremes, proposing a field that can flip between quintessence-like and phantom-like phases depending on conditions. Think of it as a chameleon with two disguises, one benign, the other catastrophic. Why would the universe need such a duality? Observations hint that dark energy's behavior might not be static. Ancient supernovas suggest its strength could have varied over cosmic history, subtly at first, then more dramatically. A pure quintessence field struggles to explain the most extreme acceleration data, while pure phantom energy predicts a doomsday that might already have left detectable scars. The quantum field elegantly bridges this gap, allowing dark energy to evolve in ways that match the universe's actual timeline. The mechanics are mind-bending. In some models, the quantum field achieves this balancing act through a crossing phenomenon. Its equation of state, represented by the value W, starts above -1 like quintessence, then dips below like phantom energy, all without tearing the fabric of physics. This transition could be driven by interactions with other hidden fields, quantum effects, or even the universe's changing matter density. Imagine a roller coaster that starts climbing slowly, then plummets, except the track is made of spacetime itself and the cart is the cosmos. The implications are staggering. If the quantum field exists, the universe's fate might hinge on which aspect of the field dominates next. Current data suggests we're in a quintessence-like phase, but a shift toward phantom behavior could trigger irreversible acceleration. Some theories even propose resonance effects where the field's oscillations synchronize with cosmic structures, amplifying dark energy's influence in local pockets while leaving other regions untouched. This could explain why some galaxy clusters seem to be flying apart faster than others, a discrepancy that puzzles astronomers. Detecting the quantum field requires next-generation cosmic archaeology. Upcoming telescopes like the Vera Rubin Observatory will map millions of supernova, tracing how dark energy's strength has fluctuated over billions of years. Others will analyze the large-scale distribution of galaxies for patterns that only a hybrid field could imprint. The most tantalizing clues might come from the cosmic microwave background's polarization patterns, subtle swirls that could encode the moment the quantum field crossed over from gentle to deadly. Critics argue the theory introduces unnecessary complexity, favoring simpler models until evidence demands otherwise. Yet the quantum field's proponents counter that nature often prefers nuance. Electromagnetism unites electricity and magnetism, and the Higgs field gives mass while interacting with others. Why wouldn't dark energy, the universe's dominant force, also be a composite of deeper phenomena? What makes this idea so compelling is its humility. Instead of forcing dark energy into a single box, it embraces the universe's complexity, suggesting that even the most mysterious forces might be shapeshifters, changing their nature as the cosmos ages. Whether the quantum field is real or not, it challenges us to think beyond static explanations, to imagine a universe where even the laws governing expansion aren't set in stone, but written in something far more fluid, the dance of hidden fields. In the realm of theoretical physics, where even the wildest ideas get a fair hearing, tachyons stand out as one of the most tantalizing and controversial concepts ever proposed. These hypothetical particles don't just break the cosmic speed limit, they're born already moving faster than light, as if the universe handed them a cheat code to bypass Einstein's rules entirely. But here's where it gets even stranger. Tachyons aren't just oddball particles, they might be the carriers of a hidden field that twists causality itself, rewriting how cause and effect play out across the fabric of spacetime. Imagine throwing a rock into a pond and seeing the ripples spread outward, except in this case, the ripples move faster than the rock's impact, appearing before the splash even happens. That's the bizarre world of tachyon fields. Unlike ordinary particles that gain energy as they accelerate, tachyons would lose energy the faster they go, approaching infinite speed as their energy drops to zero. This inversion of normal physics suggests they're not just moving through spacetime, they might be threading it differently, weaving connections that defy our everyday experience of time flowing in one direction. The implications for causality are mind-bending. If tachyons exist, they could theoretically send signals backward in time, creating loops where effects precede causes. Picture a game of cosmic telephone where the message arrives before you pick up the receiver. Some theories propose that tachyon fields might act as a kind of causal glue, stabilizing these loops to prevent paradoxes, like a self-correcting mechanism that ensures the universe doesn't unravel when time gets tangled. Others speculate these fields could explain quantum entanglement's spooky action at a distance, with tachyons zipping instantaneously between particles to maintain their eerie synchronization. But tachyons aren't just about time shenanigans, they might also hold the key to spacetime's very structure. In certain unified field theories, tachyon fields emerge as unstable configurations that trigger phase transitions, like cosmic sparks igniting shifts in the vacuum of space. During the Big Bang, such a field could have driven the universe from a chaotic, symmetrical state into the broken symmetries we see today, where forces like electromagnetism and the weak nuclear force split apart. It's as if tachyons were the universe's demolition crew, tearing down the old order to make room for the diversity of particles and forces we now take for granted. The hunt for tachyon fields is as creative as the theories themselves. Particle accelerators search for unusual energy signatures that might hint at faster-than-light decay products, while astrophysicists scan gamma-ray bursts for anomalies that could betray tachyon interactions. Even black holes, those cosmic laboratories for extreme physics, might emit tachyon-like radiation under certain conditions, offering indirect clues. So far, no smoking gun has emerged, but absence of evidence isn't evidence of absence. Tachyons, by their very nature, would be maddeningly difficult to detect, leaving only faint echoes in the data for those patient enough to look. What makes the tachyon field hypothesis so compelling isn't just its defiance of convention, it's the way it forces us to rethink the boundaries of the possible. If confirmed, it would mean causality isn't the ironclad rule we assumed, but a local phenomenon in a much weirder cosmos where time is more fluid, connections more mysterious, and the speed of light less a barrier than a suggestion. Whether tachyons are out there or not, their ghostly presence in the equations reminds us that reality might still have surprises up its sleeve, waiting for us to look past the limits of light and glimpse what lies beyond. At the very edge of what we can measure, in a realm so tiny it makes atoms look like planets, lies the Planck scale. This is the universe's ultimate resolution limit, where distances shrink to 10 to the power of -35 meters, and time ticks in incomprehensibly short intervals of 10 to the power of -43 seconds. Here, gravity and quantum mechanics cease to play nice, and spacetime itself might dissolve into a seething foam of quantum fluctuations. But hidden within this chaos could be the Planckian field, a structure so fundamental. It doesn't just operate at this scale, it might define the very rules of reality. Think of the Planck scale as the universe's deepest code, written in a language we're still deciphering. Just as pixels on a screen blend into smooth images at a distance, the Planckian field could be the hidden grid that makes spacetime appear continuous to our clumsy human measurements. Some theories suggest this field isn't made of particles or waves, but of discrete atoms of spacetime, tiny loops, spins, or even geometric shapes that weave together like cosmic chainmail. Reach this scale, and the smooth fabric of relativity might give way to a pixelated reality where concepts like here and now lose all meaning. The implications are staggering. If the Planckian field exists, it could be the missing link between quantum mechanics and gravity. Picture two dancers moving in perfect sync, except one's dancing to jazz, the other to classical. That's the disconnect between these two pillars of physics. But if the Planckian field governs how spacetime curves at the tiniest levels, it might finally reveal the shared rhythm unifying them. Some models propose this field generates spacetime's elasticity, like an invisible scaffold that stiffens or relaxes based on quantum activity. Others speculate it could explain dark energy's repulsive force, not as an external push, but as the Planckian field's natural tension at cosmic scales. Experiments to probe this domain sound like science fiction. We'd need particle accelerators the size of galaxies to directly observe Planck scale effects. But nature provides its own laboratories. The aftermath of black hole collisions might encode Planckian signatures in gravitational waves, while the cosmic microwave background could hide echoes of spacetime's quantum graininess. Even more radical are tabletop experiments using ultra-cold quantum fluids materials where ripples mimic spacetime's behavior, allowing us to simulate Planck-scale physics in a lab. What makes the Planckian field so electrifying isn't just its potential to unify physics, it's the possibility that our universe is a hologram. If this field operates like a cosmic projector, translating higher dimensional information into our 3D reality, then everything we experience might be a shadow of deeper processes. The laws of physics wouldn't be absolute, they'd be emergent properties of this underlying field, like the laws of chemistry emerging from quantum mechanics. Yet the greatest mystery remains: does the Planckian field have a voice in the larger cosmos, or is it forever locked in the quantum noise? If it interacts with larger scales, even subtly, we might find its fingerprints in anomalies, particles that flicker unpredictably, gravity that fluctuates where it shouldn't. Until then, this field remains physics' ultimate frontier, a whisper at the edge of comprehension, hinting that reality's truest shape lies waiting where space, time, and quantum uncertainty finally collide. The holographic principle turns our intuition about reality inside out. It suggests that all the information in our three-dimensional universe, from swirling galaxies to the synapses firing in your brain, might actually be encoded on a two-dimensional surface at the cosmic edge. Think of it like a credit card hologram. The illusion of depth emerges from flat, patterned foil. But what if this isn't just an analogy? What if a hidden holographic field actively translates lower dimensional data into the rich, textured world we experience? This isn't just about storage, it's about creation. Every particle collision, every supernova's light, even your thoughts, might be projections from a fundamental field operating on a boundary we can't see. The math behind this is both elegant and alien. String theorists discovered that the equations describing a volume of space perfectly match those for interactions happening on its enclosing surface, like discovering the blueprint for a cathedral is etched into its outer walls. In this view, the holographic field isn't just a passive recorder, it's a dynamic processor constantly updating reality's parameters. Black holes cement the idea. Their entropy, a measure of hidden information, scales with their surface area, not their volume. It's as if the universe enforces a cosmic pixel limit, with the holographic field acting as the compression algorithm that keeps everything running smoothly. Quantum entanglement offers a tantalizing clue about how this field might operate. When particles become entangled, measuring one instantly affects its partner, regardless of distance. This spooky action could reflect updates propagating through the holographic field's underlying code, like two characters in a video game reacting simultaneously because they're rendered by the same engine. Experiments with entangled photons show correlations that classical physics can't explain, but which holographic models predict with eerie accuracy. The field wouldn't just store information, it would mediate it, weaving locality and non-locality into a cohesive whole. Practical implications ripple across disciplines. In condensed matter physics, researchers simulate holographic principles to explain high-temperature superconductivity materials that conduct electricity perfectly under conditions that defy conventional theory. The holographic field's mathematical tools describe electron interactions as projections from a higher dimensional space, suggesting that our 3D reality might be the shadow of processes occurring in dimensions we can't access. Similarly, neuroscientists explore whether the brain's neural networks might leverage holographic encoding, with memories and perceptions distributed across neuronal surfaces rather than stored in isolated clusters. The most radical possibility, the holographic field could redefine causality itself. If time emerges from how information is processed on the boundary, then past, present, and future might be simultaneous in the field's source code. This aligns with oddities in quantum mechanics, where particles seem to know about future measurement settings in delayed choice experiments. The field wouldn't just encode space, it might render time as an experiential layer, like a video game loading only the scenery a player currently sees. While skeptics argue the holographic principle remains untested metaphysics, upcoming quantum gravity experiments aim to probe its predictions. Devices like holometers check for space-time pixelation at Planck scales, while others analyze cosmic microwave background patterns for signs of hidden dimensional data. Whether the holographic field is real or not, it forces a profound shift in perspective. The universe's true canvas might not be the world we see, but an invisible surface where reality is written in light, information, and something stranger still. The possibility that depth itself is the ultimate illusion. Empty space is anything but empty. Quantum theory insists that even in a perfect vacuum, particles flicker in and out of existence in an endless dance. But what if these fleeting fluctuations aren't just background noise? Beneath the chaos lies a deeper secret, the vacuum expectation value, a subtle yet persistent energy that fills every cubic inch of the cosmos like an invisible tide. This isn't just theoretical jargon, it's the reason particles have mass, forces have range, and the universe might be fated to expand forever. Picture a calm lake at dawn. On the surface, it appears perfectly still, but dip your hand beneath and you'll feel currents, persistent, directional flows hidden from view. The vacuum expectation value works similarly. Quantum fields aren't just vibrating randomly. They have baseline energy levels, non-zero values they expect to maintain even in their lowest energy state. The Higgs field is the most famous example. Its vacuum expectation value is what gives particles mass by resisting their motion, like wading through cosmic molasses. But the Higgs might be just one player in a larger symphony of fields, each contributing its own hidden energy to the vacuum. These values aren't just mathematical quirks, they shape the universe's evolution. When physicists calculate the vacuum's energy density, they stumble upon a paradox. Quantum theory predicts a value so enormous, it should have ripped space-time apart moments after the Big Bang. Yet observations show the actual energy is a staggering 120 orders of magnitude smaller. This cosmological constant problem is the greatest mismatch in science, and hidden fields might hold the key. Some theories propose cancelling mechanisms opposing fields whose energies neatly offset, leaving just a whisper of dark energy behind. Others suggest dynamical fields that adjust their vacuum values over cosmic time, like a thermostat fine-tuning the universe's expansion rate. The most startling implication: vacuum expectation values might not be constants at all. During the universe's first moments, phase transitions could have shifted these hidden energies abruptly, like water freezing into ice. These cosmic snapshots might still echo in the distribution of galaxies or the polarization of the cosmic microwave background. Future gravitational wave detectors could hunt for relics of these transitions, ripples in spacetime from when the vacuum itself changed state. What makes this concept so profound is its duality. The vacuum expectation value is both the hum of nothingness and the scaffold of reality, a reminder that even emptiness has structure, and the universe's grandest mysteries might be written in the silent language of hidden fields. Imagine a universe where all the forces of nature were once united, a perfect, symmetrical state where electromagnetism, gravity, and the nuclear forces were indistinguishable, bound together like threads in a seamless tapestry. This wasn't just a hypothetical scenario, it was the reality of the cosmos mere instants after the Big Bang. Then something extraordinary happened. Hidden fields, like invisible hands, began tugging at this symmetry, unraveling the unity and giving rise to the distinct forces we recognize today. This process, known as symmetry breaking, didn't just reshape the universe, it made life and complexity possible. At the heart of this cosmic transformation lies the symmetry breaking field, an enigmatic structure theorized to govern phase transitions in the early universe. Think of it like cooling water. As temperatures drop, the liquid's symmetrical, uniform state gives way to ice crystals with rigid, orderly structures. The water hasn't disappeared, its potential has been funneled into a new, less symmetrical form. In the universe's infancy, something eerily similar occurred. As temperatures plummeted from trillions of degrees, hidden fields shifted their energy states, forcing the fundamental forces to choose their separate paths. The electromagnetic force peeled away from the weak nuclear force, while gravity and the strong nuclear force carved out their own domains. The mathematics behind these transitions reveals something profound. Symmetry breaking didn't just alter the forces, it birthed the particles themselves. Take the Higgs field's role in electroweak symmetry breaking. Before this transition, particles like photons and W and Z bosons were identical, massless entities. But as the Higgs field settled into its new state, photons remained massless, while W and Z bosons suddenly gained mass, defining the weak nuclear force's short-range behavior. This wasn't random chance, it was orchestrated by the symmetry-breaking field's dynamics, like a conductor silencing certain instruments so others could be heard. These transitions didn't happen smoothly. Theorists propose that the universe endured violent phase changes, where bubbles of the new state nucleated and expanded at nearly light speed, colliding in shockwaves that might have left gravitational echoes detectable today. Some models even suggest these cosmic tremors could explain the universe's mysterious matter-antimatter imbalance, that the symmetry-breaking field, as it decayed, subtly favored matter over antimatter, gifting us a cosmos with galaxies rather than empty radiation. Evidence for these cataclysms might be hiding in the cosmic microwave background's faintest patterns. Just as imperfections in glass reveal how it cooled, the CMB's temperature fluctuations could encode the moment when hidden fields reconfigured reality. Future gravitational wave detectors, like the proposed Big Bang Observer, might also capture the reverberations of long-ago phase transitions, ripples in space-time from when the universe changed its fundamental rules. What makes symmetry-breaking fields so mesmerizing is their dual nature. They're both destroyers and creators, shattering primordial unity, yet forging the diversity that allows atoms, stars, and minds to exist. Without them, the universe would have remained a featureless soup of indistinct energy. Instead, these hidden architects sculpted the cosmos into a realm rich enough for galaxies to spin, particles to bond, and life to question its own origins. And somewhere in the quantum whispers of the vacuum, their legacy lingers, a reminder that sometimes breaking symmetry isn't loss, it's how complexity begins. Deep in the cosmic shadows, something bizarre is happening. Galaxy clusters, enormous structures containing thousands of galaxies, aren't just drifting apart with the universe's expansion. They're also moving together in a coordinated rush toward a single point beyond the edge of the observable universe, as if pulled by an invisible hand. Astronomers call this phenomenon the dark flow, and it's one of the most unsettling mysteries in modern cosmology. If confirmed, it wouldn't just defy expectations. It would suggest the existence of a hidden field so vast and powerful that its influence stretches beyond the limits of what we can see. The discovery came from analyzing the cosmic microwave background, the afterglow of the Big Bang. Tiny temperature shifts in this ancient light reveal how galaxy clusters move relative to the universe's expansion. But in 2008, researchers noticed something odd. Hundreds of clusters were streaming at breakneck speeds, up to 1,000 kilometers per second, toward the same patch of sky. It wasn't just random motion, this was a cosmic current flowing against the tide of expansion. The strangest part, the direction they're moving points toward nothing we can detect. No supercluster, no massive attractor. Just empty space. Mainstream cosmology struggles to explain this. Gravity's pull weakens with distance, so even the most enormous structures shouldn't exert influence beyond a few 100 million light-years. Yet the dark flow spans billions of light-years, hinting at forces operating on scales we can't yet comprehend. One radical possibility, a hidden field far beyond our observable universe, is warping space-time on a cosmic scale, not with gravity as we know it, but with something stranger. Imagine dropping ink into a still pond and watching the droplets suddenly rush toward one edge. That's the dark flow's mystery. Something out there is tilting the playing field. The implications are staggering. If this field exists, it could mean our universe isn't the smooth, uniform expanse we thought. Beyond our cosmic horizon, there might be regions where physics operates differently, alternate bubbles of reality with stronger fields, higher dimensions, or even other universes exerting gravitational drag. Some theories suggest the dark flow could be evidence of a collision with another universe in the multiverse, their boundaries brushing just enough to tug our galaxy clusters toward them. Others propose a primordial tilt in the fabric of space-time, frozen in during the Big Bang and only now revealing itself through the motion of galaxies. Skeptics argue the dark flow could be a measurement error, a subtle distortion in the cosmic microwave background mimicking motion, but repeated studies, including analyses from the Planck satellite, keep finding the same eerie signal. If it's real, this isn't just a curiosity, it's a crack in our understanding of cosmic boundaries. The dark flow field, if it exists, wouldn't just tug on galaxies. It could rewrite the rules of where the universe ends and what lies beyond. The hunt for answers is pushing telescopes and simulations to their limits. Future galaxy surveys will map the flow's trajectory more precisely, while quantum gravity models explore how hidden fields might propagate influence across unfathomable distances. One thing's certain, if the dark flow is truly pointing to something beyond our cosmic horizon, then the universe's greatest secrets might not lie in what we can see, but in the invisible currents pulling us toward the unknown. Quantum mechanics has always played by bizarre rules, particles existing as probability waves, cats both dead and alive, reality seemingly undecided until someone takes a look. But here's the million-dollar question. What exactly counts as an observer capable of collapsing these quantum possibilities into concrete reality? The conventional answer points to detectors, lab equipment, any interaction that leaves a mark. Yet a radical alternative lingers at the edges of physics, one that suggests consciousness itself might be the missing ingredient. Not just human minds, but a fundamental consciousness-induced field woven into the fabric of reality, a hidden medium through which observation truly shapes existence. This idea isn't new. Nobel laureate Eugene Wigner first proposed that consciousness might play a role in quantum collapse, arguing that even a detector's measurement requires a conscious observer to complete the chain. But take this further, and you arrive at something far grander, a universal field where subjective experience isn't an emergent property of brains, but a foundational force like gravity. Picture the double-slit experiment where particles behave as waves unless observed, then abruptly choose a path. If consciousness is the catalyst, then the field mediating it wouldn't just be passive. It would actively negotiate between possibility and actuality, like a cosmic director whispering cues to reality's actors. Critics dismiss this as mysticism masquerading as science, and for good reason. Mainstream interpretations like decoherence theory explain wave function collapse through environmental interactions, no consciousness required. Yet puzzles remain. In delayed choice experiments, particles seemingly, retroactively adjust their behavior based on future observations, as if the universe is running on a script that only makes sense in reverse. Some quantum anesthesia studies even hint that anesthetic agents which suppress consciousness might subtly alter quantum processes in microtubules, the tiny structures inside neurons. If true, it suggests a bizarre feedback loop where consciousness and quantum physics are entangled at levels we've barely begun to probe. The wildest implications emerge in cosmology. If a consciousness field exists, could it have played a role in the universe's early moments? The Big Bang's initial conditions were finely tuned to an almost impossible degree, a fact often chalked up to multiverse luck or divine intervention. But what if the act of observation itself, mediated by this field, somehow stabilized those conditions? In this view, the universe isn't just here. It's here because something, perhaps even future observers, participated in its becoming. The anthropic principle, the idea that the universe's laws permit conscious life, takes on eerie new dimensions when the observers aren't just beneficiaries of cosmic fine-tuning, but active collaborators in its unfolding. Neuroscience adds another layer. Brain activity shows signatures of quantum coherence, electrons tunneling across synapses, microtubules vibrating in ways that resemble quantum computations. If these processes interface with a consciousness field, it might explain the brain's staggering efficiency at solving problems that stump supercomputers. Near-death experiences where patients report lucid awareness during clinical brain death could reflect temporary disentanglement from this field, like a radio losing signal but still picking up distant stations. Even placebo effects, where belief alone triggers physiological healing, might be evidence of the field's ability to bridge mind and matter at fundamental levels. Experiments to test this border on science fiction. Quantum cognition studies explore whether human decision-making exploits quantum probability, while global consciousness projects analyze random number generators for anomalies during mass meditative events. The most tantalizing work involves consciousness detectors, devices designed to isolate quantum systems from all environmental noise except potential field interactions. If such an experiment ever registered collapse without physical intervention, it would ignite a revolution rivaling relativity's birth. What makes the consciousness-induced field hypothesis so electrifying isn't just its defiance of convention, it's the way it reframes our place in the cosmos. We're not just passengers in a predetermined universe, but participants in a grand, dynamic exchange between observation and reality. Whether this field exists or not, its possibility stretches science to the edge of philosophy, challenging us to ask, if a tree falls in a quantum forest, does it make a sound, or does it wait for someone to listen? What if everything around us, every star, every atom, every thought isn't fundamental at all, but lines of code in an inconceivably advanced simulation? The simulation field theory takes this sci-fi staple and gives it a physics twist. Hidden fields might not just influence reality, they could be the reality, acting as the underlying programming that dictates how the universe processes information. Think of these fields not as forces or particles, but as the source code of existence itself, with equations like Einstein's relativity or quantum mechanics serving as the simulated rules baked into the system. This isn't just philosophical speculation. Some physicists argue that if we live in a simulation, there would be detectable artifacts, tiny glitches or optimizations in how the cosmos operates. For instance, the universe's pixelation might reveal itself at the Planck scale, where space-time could appear grainy under extreme magnification, like a video game's textures when viewed too closely. Quantum indeterminacy, the way particles exist in superpositions until measured, might reflect processing limitations, with the simulation only rendering precise states when absolutely necessary to conserve computational power. Even the speed of light could be a built-in frame rate, preventing the system from overloading by imposing a strict limit on how quickly information propagates. The role of hidden fields in this model becomes fascinatingly meta. Instead of mediating forces, they might function as the simulation's memory allocation or data structures. Dark energy's mysterious push could be a background process ensuring the simulation's expansion doesn't crash, while quantum fields like the Higgs might be subroutines assigning properties to particles on the fly. In this view, the laws of physics are just elegant abstractions over much deeper algorithmic layers, an API for reality, with hidden fields as the undocumented functions that only the universe's programmer fully understands. Evidence could lurk in unexpected places. High-energy cosmic rays sometimes arrive with energies that should have been dampened by interactions with the cosmic microwave background, unless spacetime itself has subtle discretization, like rounding errors in a numerical simulation. Certain patterns in the cosmic microwave background might also hint at underlying mathematical symmetries too perfect for randomness, resembling the procedural generation seen in open-world video games. Even quantum entanglements, instantaneous connections, could make sense if the simulation simply updates correlated variables without needing to transmit information between them, like a program changing two linked cells in a spreadsheet at once. Critics argue this is unfalsifiable metaphysics, but proponents counter that science has historically expanded to include once unthinkable layers, from atoms to quantum fields to higher dimensions. If the simulation hypothesis is true, hidden fields might be our first glimpse of the compiler behind the cosmos, a shadow of the machinery humming beneath the illusion. Whether a daring metaphor or a literal truth, this idea forces us to ask, if reality is code, what else might be written in its scripting language? The answer could rewrite not just physics, but our very sense of what it means to exist. From the quantum whispers of zero-point energy to the cosmic choreography of dark flow fields, we've journeyed through 30 mind-bending theories that rewrite reality's rulebook. Each one suggests that hidden fields aren't just scientific curiosities, they could be the unseen architects of existence itself, shaping everything from the spin of electrons to the fate of galaxies. Think of these fields as the universe's backstage crew, quietly adjusting the dials on gravity, time, and even consciousness while we only see the final performance. Consider how radical this shift would be. For centuries, we've described reality as particles and forces colliding in empty space. But if fields like the inflaton or quintessence are real, then empty space is a myth, a vibrant, dynamic medium humming with activity. The Higgs field already proves this. It's why you have mass, why stars ignite, why the cosmos isn't just a featureless void. Now imagine discovering that dark energy is a field evolving over time, or that action fields are the invisible hands guiding dark matter. Suddenly, the universe transforms from a collection of objects into a living, breathing network of interconnected influences. Some theories feel tantalizingly close, like torsion fields that might explain quantum entanglement, or Planckian fields stitching spacetime together at the tiniest scales. Others stretch the imagination further, consciousness-induced fields blending mind and physics, or simulation fields suggesting reality itself might be code. Yet even the wildest ideas share a thread of mathematical elegance, hinting that nature prefers unity over randomness. Whether it's the elegance of string theories, vibrating filaments, or the haunting beauty of holographic fields encoding 3D reality on 2D surfaces, these ideas push us to see the cosmos not as a machine, but as a symphony with hidden fields as its harmonies. So which theory resonates with you? Maybe it's the haunting possibility of phantom energy dooming the cosmos to a big rip, or the hopeful vision of cyclical universes reborn through ekpyrotic collisions. Perhaps you're drawn to the practical, how chameleon fields could redefine gravity, or how biophotons might revolutionize medicine. Whatever captivates you, remember, every revolutionary idea in science was once deemed impossible, from continental drift to black holes. The next paradigm shift could be hiding in these very theories, waiting for a curious mind to connect the dots. The conversation doesn't end here. Which of these hidden fields do you think holds the most promise or the most peril? Drop your thoughts below and let's keep unraveling the universe's greatest mysteries together. After all, the most exciting discoveries often begin with a simple question.